So we'll discuss today optical parametric oscillators or OPOs. So we had discussed four-way mixing and how it can be used to give gain to optical signals, right, or amplify weak optical signals, and how we can use them to build optical parametric amplifiers. Okay. So whenever you have an amplifier, if you put an amplifier or gain medium within an optical cavity, you can get oscillation, okay, due to the feedback in the cavity. And so similarly, with this nonlinear amplifier also, you can place or like have the nonlinear gain happening inside an optical cavity, and it can lead to oscillation. So for example, you know how a laser is built, right? Like you have some gain medium and then you put it inside some optical cavity, and when the gain exceeds the losses in the cavity, then you start getting lasing, right? So concept is similar here, right? So imagine you have an optical cavity, okay, then you have some Dielectric medium here, right? And let's say we pump it with a strong laser at some frequency omega p, right? So this cavity, of course, has resonances, right? And so let's say we pump at one of the cavity resonances. So the field builds up inside the cavity, right? And the intensity becomes large. And then if the conditions are set up right, like for example, we have discussed dispersion, etc. If those conditions are set up right inside the cavity, then you can get this four-way mixing process to happen within the cavity. Right, so this degenerate pump four-way mixing. So the pump photons are converted to signal and idler photons. So in an OPA, we had seen that, so we send in a pump, a strong pump, right? So it's typically some waveguide or fiber. So you are freely propagating fields. And typically we saw for an amplifier at the input, we send in a strong pump and a weak signal. And then as the fields propagate, the signal gets amplified and an idler is generated also in the process, right? So now this process is happening within the cavity, and at the input, we are not sending any signal or idler, we're just sending in the pump, right? So if the gain due to this four-way mixing process becomes large enough, such that, so let's say you can imagine you have some round trip gain here, right? And if that round trip gain becomes more than the round trip loss in the cavity, so the losses could be, let's say, propagation loss within the medium, the mirror reflectivities, etc. Right? Then any small noise at these signal or idler frequencies will get amplified, right? So they will start from noise and get a huge amplification, and at the output, you can actually get just like a laser, you can get coherent light coming out of the cavity. Okay, so it's similar to like a laser gain medium, right? So in a laser, what we have is a gain medium inside an optical cavity, and then we pump it. The pumping mechanism can be either optical or other means, right? And we create some population inversion within this medium in the cavity, and that leads to amplification, right, of fields inside. And then again, the same concept: gain exceeds loss, then you get coherent light out, right? So similar concept here. So You can think of this as a laser operating at omega s or omega I, right, or both. And omega t is actually
Sir, we are not able to see the video.
hello. Can you now hear me?
Yes, sir. Now it's okay.
Okay. Can you also see?
Yes, sir.
Yes, sir.
Yeah, okay, I don't know what the issue was, but okay. So I don't know where you stopped hearing me. So yeah, basically maybe I start again. So the idea is if so we have discussed optical parametric amplification using four-way mixing, right? So where we send in a strong pump and then a weak signal, and as it propagates, as the fields propagate along the nonlinear medium, which could be like a fiber or waveguide, then the signal gets amplified, and in the process you generate an idler, right? So just like a laser, if you place this nonlinear medium or this nonlinear amplification happens inside a cavity, then if the gain due to this nonlinear process exceeds the losses in the cavity, then you can get coherent light out at the signal and idler wavelength, just like a laser. So if the gain for the signal and idler within the cavity due to this nonlinear process exceeds the losses that the signal and idler experience in the cavity, then sort of signal and idler can laze. So if you plot the signal and idler output power as a function of the pump power, you get this threshold kind of behavior which looks exactly like a laser. So initially, for low pump powers there is no output, right? But as soon as you cross a particular threshold, then you start getting finite power or coherent light at the signal and idler wavelengths, right? So this is some threshold power, so just like a laser. Okay, and so basically we're not sending any signal or idler, we're just pumping with the pump frequency. But beyond a particular pump threshold power, basically you get bright light at signal and idler wavelengths, just which are just starting from quantum noise or vacuum fluctuations within the cavity, just like a laser. So typically this kind of setup is done in a ring cavity. So either in a fiber-based ring cavity. So you send in your input pump power from here, okay, and then this four-way mixing. Then you have some coupler here, right? So this is a fiber beam splitter, or this could be made on a chip. So these are waveguides, for example, right? And then the coupling here takes place evanescently. So these waveguides are close to each other, and there is some evanescent coupling. So you get some coupling into the ring, right? And so this is a ring cavity, and then four-way mixing happens inside this ring. And then if you are above the threshold power, then at the output you get the signal and idler coming out. Okay. So this was first done with fiber-based ring cavities, but recently people have done it with very small micron scale devices on a chip, right? And so those are called micro resonators because they are micron scale, and it's an optical resonator which is of the scale of micron, so it's called micro resonator. So people have now demonstrated these kinds of things in micro resonators on a optical chip. Okay, so so basically this coupler here has so just like in a Fabry-Perot cavity, right? You have some reflectivity and transmittivity for the mirrors. So here in the ring cavity, this coupler here, so you can imagine the straight through port is like a reflection, right? And then the coupling to the other port is like a transmission. Right? So the transmission is the one which gets from outside to inside the cavity. So that's the coupling from this coupling waveguide into the ring. That's the transmission coefficient. And then the part which just stays out is the reflection which comes back, right? So you can think of this coupling region also as like a mirror or a beam splitter with some reflectivity and transmittivity. Where again R plus T is 1, right? If this region is lossless. So we had already, so in the last class, so for both the fabric cavity and the ring cavity, we had calculated last time what is the intensity enhancement inside the cavity, right, as compared to the intensity which is sent in at the input, right, or equivalent to the power enhancement. So PC is the power in the cavity, and P in is the power sent in here. So let's say PC. Right. So let's say now we are looking at the pump frequency because we are only sending in the pump, right? So we send in some input power P in, and then it gets coupled into the cavity, and then it builds up within the cavity due to multiple round trips. And then the cavity, the power in the cavity is related to the power in steady state. The power in the cavity is related to the power input. If you recall, we had derived this expression, right? 1 over T 1 plus 4R over T square, and then the sine square factor. Right. So recall last time we had derived this expression. So it goes as sine square of this phase phi r by 2. So phi r is the round trip phase. Right. Basically the phase acquired by the field in one round trip of the cavity. And so we can write this as beta times LR. Right. So if LR is the length, so length of this ring cavity is LR, then if there is some propagation constant beta, right? So we know that the phase goes as e to the I beta z. So in one round trip, the phase acquired is beta times LR. Right? So this is the propagation constant.
LR is the length of the fiber.
Yeah, LR is the round trip length of this cavity. So many times, for example, this is just made like a circle of some radius r. So then LR is just 2 pi r. But it could be whatever shape, like in a fiber, it could be wound up in whatever shape. But basically, LR is the total length, round trip length. Just wait 1 minute. There is some noise from outside. Sorry, is the background noise too much? They're doing some work downstairs in the building. Okay. Yes. So now, just like a laser, if you want an efficient oscillator here, then we want this cavity to be good, which means the mirrors need to have very high reflectivity, right? Or equivalently, this transmittivity has to be very low. So so for a good cavity, so this reflectivity has to be almost 100%. Okay, so basically we can just replace R by 1 here. Okay, so the first approximation we make, that is for a good cavity, we want good mirrors, so the reflectivity is almost 100%, right? So basically we put R or approximate R by 1 here, so we get 4 by t square, and then we define this quantity f, which is pi by t, right? So that's called the finesse of the cavity. So you might have also heard about this in your basic optics course when you learned about optical resonators. So there is this quantity called finesse, which is defined as this. Okay, and so then we can write the power enhancement in the cavity in terms of this finesse. Okay, and this finesse is basically roughly the number of round trips that a photon takes in the cavity before it leaks out. Okay, so you can see that t is a very small number, right? So let's say t is like 0.01 or something. So the finesse would then be of the order of 100. So that means that a photon like makes hundreds of round trips before leaking out. And you can imagine that the more round trip it makes, the more gain it can experience, right? So yeah. So this finesse is roughly the number of round trips before leaking out. Okay. So basically, you want to do this in a good cavity with very low T or very high finesse, right? Which leads to basically a very high power in the cavity, right? And we had studied when we were discussing four-way mixing that that the gain goes nonlinearly with the compound, right? So if, for example, you have a perfectly phase match process, then we saw that the gain actually goes exponentially with the pump power. So the more you can enhance the power in the cavity, the lower would be your threshold power. Okay, so now,
Sir,
yeah.
how can we increase this F number?
So it just depends on T here, right?
Okay.
So you want, so in the case of a fabric arrow cavity, that means the mirrors have very high reflectivity and very low transmittivity, right? So 99% or 99.9% reflecting. So T is like 0.1, 0.01.
So basically, it only depends on the reflectivity of the mirrors.
Yeah.
Kind of.
I mean, if there is some loss, propagation loss within the cavity, then that also sort of factors in. But yeah, for now, let's say that the propagation loss within the cavity is small compared to the what you're getting from the reflectivity. So then it just depends on the.
Okay. Thank you.
Okay. Right, and so basically, whenever this phi r becomes a multiple of pi, then this factor becomes 0, and then you can see that the power in the cavity is a factor of finesse times my input power. Right. So on resonance, so whenever phi r, the round trip becomes a multiple of pi, then the power in the cavity is enhanced by a factor of the finesse. Right. So basically, you know that if we so look at the power in the cavity as a function of this phase phi r, which is like a function of frequency or something, right? Then so if I plot the power in the cavity, so as a function of phi r, so this phi r is again beta times Lr, right? So this is omega over c times n effective times Lr. So for example, you can plot it as a function of frequency, the other things remaining constant. Then you see these resonances, right? So whenever phi r becomes a multiple of pi, you get a peak. And this peak value is basically f by pi times Pn. Right? So you get these resonances. And so if you look at the mth resonance of the cavity, that's given by the condition when the round trip phase becomes 2m pi. Okay, so yeah, so we have phi r by 2 here. So whenever this argument becomes a multiple of pi, which means phi r is a multiple of 2 pi, then this factor becomes 0 and you get power enhancement. So if we look at the mth resonance, that means the mth multiple of 2 pi is the round trip phase, right? So this means that the condition is right. So let's say this mth resonance is occurring at a frequency omega m. Okay, so then this beta m is basically the beta at the frequency omega, right? So we will have a resonance at the frequency omega m if beta at that frequency times the round trip length is a multiple of 2 pi. Okay, and then some terminology here which you also might be familiar with. So the spacing between two consecutive resonances is called the free spectral range, or FSR. Okay, so if I write the um, so from this condition, right? So the mth resonance frequency. So you know here, right? I can write beta at omega m as omega m, which is, let's say, 2 pi nu m divided by c times n effective times LR. This is 2m pi, right? So the 2 pi's get cancelled, and then we get an expression for the mth resonance frequency nu m is m times c over n effective times LR, right? So that's the mth resonance frequency. So instead of omega, I'm using nu here. So nu m is m times c over n effective times LR. Right? Similarly, this will be nu m plus 1. So m plus 1th resonance. Right? And then the spacing between the two is the free spectral range. Okay, so we can also try to compute the free spectral range in terms of these cavity parameters. So for the m plus, so we have this for the mth resonance. For the m plus 1th resonance, we'll have beta m plus 1 times LR is equal to m plus 1 times 2 pi. Okay. Right? So now we can just subtract these two equations for the m and m plus 1th resonance. So if we subtract the two, then we get that beta m plus 1 minus beta m is 2 pi times or over LR. Right? So when I subtract m plus 1 times 2 pi and m times 2 pi, I remain with 2 pi. So I get this. Okay, and so beta m plus 1 now is beta at omega m plus 1, and beta m is the beta at omega m. So we can now again use the scalar expansion for beta. Remember, so when we were discussing dispersion and phase matching for four-way mixing, then we use the scalar expansion of the beta around the pump frequency. We can use the same concept here. Okay. So basically, we want to get these in terms of the dispersion parameters, right, of the fiber or the waveguide that we've used to make our cavity. So beta m plus 1 is basically beta at the frequency omega m plus 1. That I can write as beta at the frequency omega. So I do a Taylor expansion about omega m, and then beta 1 times omega m plus 1 minus omega m. Right, and this beta 1 is basically the first derivative of this beta, which is 1 over the root velocity. And the group velocity I can write as C over Ng, where Ng is the group index. Just we have like a phase index, so that N effective was the phase index, the usual refractive index. Just like that, we can define a group index, which is basically, so gives the group velocity as C over Ng. So this is the group index. Right, so in general, this group index Ng will be different from the phase index because of dispersion in the medium. So, yeah. So then beta m plus 1 minus beta m is, I just take this to the other side, right? So this is beta m. Beta m plus 1 minus beta m is just this. So beta 1 is given by this n group index by C. And then I have omega m plus 1 minus omega m, which is basically 2 pi times the FSR. Right? This is 2 pi nu m plus 1 minus nu m. So, and nu m plus 1 minus nu m is basically the FSR. Right? So, from there, you can get the FSR, the free spectral range of the cavity, which is the frequency difference between convective resonances, as C over Ng times Lr. Okay, so basically the point to note here is that the free spectral range depends on the group index. Okay, whereas in the individual resonances, the resonance frequencies depended on this N effective, but the FSR actually depends on Ng. Right? If you have a dispersionless cavity, which means the refractive index doesn't change with frequency at all, then this Ng is the same as N effective, and so you might recall in your basic optic course when you discussed like parametric cavities and FSR in those types of cavities, then you basically just use N without any. So use N here and N here, right? But in general, if you have dispersion, which means refractive index is a function of frequency, then the FSR will have this group index. I can also write this as 1 over beta 1 times Lr, where beta 1 is again 1 over velocity. So now you can see that if you have a constant group index, which does not depend on frequency, or in the cavity doesn't depend on frequency, then this FSR is a constant, right? Which means that no matter which two resonances I take, I will always measure the same FSR, right? So it doesn't depend on where I'm measuring, it doesn't depend on the frequency, if this is constant, right? But if Ng is also a function of frequency, or in other words, beta 1 is not a constant, then FSR is also a function of frequency, which means basically FSR doesn't remain constant, right, as I go across resonances. And when will beta 1 not be a constant? When the second derivative, so when the d beta 1 by, so again recall, we had defined the second derivative of beta, which was, so d beta 2 is d beta 1 by d omega, and this was the GVD parameter. So if this is finite, that means beta actually varies with frequency, and then the FSR is not constant, right? So if you have a finite GVD, in your cavity, then the FSR is varying with frequency, it's not constant. Right? If you have 0 GVT in the cavity, then your FSR is constant. Okay, so maybe to summarize, so 0 GVT or beta 2 equal to 0 implies FSR is constant, independent of frequency. But if GVT is finite, then the FSR actually varies with frequency. So, if beta 2 is not equal to 0, that means you don't have equally spaced resonances, right? Only if beta 2 is 0, then you have equally spaced resonances. Okay, and then you can see how fast this FSR is varying. So d nu FSR, so the variation of the FSR as a function of frequency. So we have the expression of FSR here, 1 over beta 1 times LR. So if we take the derivative with frequency, right, so the only frequency dependent quantity here is this beta 1. So I get minus 1 over beta square and then d beta 1 by d omega, which is beta 2. Yes, so you can see how the FSR changes with frequency depends on beta 2. Okay, and it also depends on the sign of beta 2. So if beta 2 is positive, then d nu FSR by d omega is negative. On the other hand, if beta 2 is negative, then d nu FSR by d omega is positive. Right? So what is d nu FSR by d omega? As I increase frequency, how is my FSR changing? Right? So if this is positive, then the FSR is increasing with higher frequencies. If this is negative, then the FSR is decreasing with higher frequencies. Right? And that depends on the sign of beta 2. So recall we had defined that dispersion was GVT as normal if beta 2 was positive, right? And anomalous if beta 2 was negative. So depending on if the medium has a normal or anomalous dispersion, the FSR will either increase or decrease with frequency. Okay, so we can see this a little bit more clearly. So if you want to say the change in FSR over one mode, so So I look at the FSR at a particular mth mode, and then go one mode over and see how much the FSR changes for the next mode. So right. So for the m plus 1th mode, the FSR is the m plus 1th frequency minus the mth frequency, and then one mode less is the mth frequency minus the m minus 1th frequency, and we want to see the difference in them. Right. So that's basically this d nu FSR by d omega times 2 pi times nu FSR, right? So that's the slope, and then we want to see how much that changes over 1 FSR. So over a delta omega equal to omega FSR, right? So if you plug in this expression for the d nu by d omega, then you get okay. So for d nu by d omega we use this, and then nu FSR also we know is 1 over beta 1 LR. Right. So finally we get when the FSR changes by this much, so 2 pi beta 2 divided by beta 1 cube L square. Okay, or I can write it in terms of, so beta 1 is basically Ng over C, right? 1 over the group velocity, so I can write it in terms of the group index also. Okay, so basically you can see how much the FSR changes. Again, is proportional to beta 2. Right, and again, if it's depending on the sign of beta 2, it's either positive or negative. Right, so what this is saying is basically, if I take 3 consecutive resonances, so this is m minus 1, this is m plus 1, then this spacing is not equal. Right, so this is nu FSR m plus 1, this FSR m, these two are not equal. So the spacing between the resonances is changing. Right, and so recall that for phase matching of the 4-wave mixing process, we wanted anomalous dispersion, right? So this beta 2, we wanted it to be negative, right? So yeah, just recall that for phase matching the 4-wave mixing process, we wanted beta 2 to be negative, which means that so in this cavity case, if we have anomalous dispersion, which we need to phase match the 4-wave mixing process, right, which is what is giving the gain within the cavity, then you can see that this delta Fs nu FSR will be positive. So if beta 2 is negative, then this is positive, which means that the FSR is increasing, as I go higher in mode number or frequency, which means so here it's small, then it becomes bigger, then it becomes even bigger, right? So for anomalous dispersion, so this is required for phase matching the Fourier mixing, right? So this implies that the FSR increases with frequency. Okay. So another way to look at it is if you take these consecutive mode numbers, right, and plot the frequency of the of those particular mode numbers. So basically you plot nu m as a function of m, right? So if you don't have any dispersion or basically beta 2 is 0, then this is a straight line, right? Which means that the modes are equally spaced, right? So this is some particular m, then m plus 1, m plus 2, and the FSI is basically constant, so it's not varying with mode number, right? So this is the case for 0 GVD, right? For anomalous GVD, what happens? The FSI is actually increasing with mode number or frequency. So this becomes like a parabola like that. Right? So the spacing between the consecutive modes, the frequency spacing keeps increasing. So this is the case of the anomalous GVD, which we need to phase match our Fourier mixing process.
Sir, the video is not on.
So yeah, this is just a linear function. But with dispersion, basically there's a second order term here also. So m square okay. So this delta FSR, which is the change in FSR between consecutive resonances, if that is finite, which happens if the beta 2 is finite, then basically the mode number also has a dependence on m square. So this is like a parabola.
Sir, you can explain what you have done here?
Okay, so you have these resonances, right?
That is okay. Just a question, sir. Just you have written around.
Yeah,
New m is equal to new.
So this straight line case is clear, right? So when you have 0 GVD, so when beta 2 is 0, that means the FSR remains constant and the resonances are equally spaced, right? Which means as a function of m, if I draw nu m, they all are in a straight line, right? So the spacing here, this is the same.
Okay, sir.
For 0 GVD, right? So this is a straight line. So for 0 GVD, the equation for the mth resonance frequency can be written as some constant plus m times. So it's an equation for a straight line, right? So the equation of nu m versus m is a straight line, right? So yeah. But when you have a finite GVD, then we know that so the FSR doesn't remain constant, right? So the FSR changes as we change mode number, right? Which means this is not a straight line anymore, right? So in the specific case of beta 2 negative, which is anomalous, this delta nu FSR is positive, which means I get an increase in the resonance frequency because this FSR is increasing as I go to higher mode numbers, right? So that's this case. So if you had normal GVD, beta 2 positive, then this will go like this, right? It will bend down. So the FSR will be decreasing with frequency. But we are only looking at the anomalous case because that's what we need to phase match the four-way mixing process, right? So we would want anomalous dispersion in our cavity. So in that case, so the modes are not equally spaced. So the mode frequency versus mode number is not a straight line, but it also has, along with the first order, it also has the second order term here, which is what is giving you this slight curve or parabolic here, right? And how did I write this? So you can check. So what is delta fs nu FSR? That's nu m plus 1 minus nu m minus nu m minus nu m minus 1, right? So you can so using this equation, you can write nu m plus 1, nu m minus 1, right? Just change m minus 1, and then compute this. You see, you will get delta nu FSR. Right? That's why it's coming. Right? Another way to see is, so basically the first derivative, so when I plot the mode frequencies versus mode number, the first derivative gives me the FSR, right? The slope is giving me how much the frequency is changing when I change mode number, right? So that's basically FSR, right? And then the second derivative gives me how the FSR is changing, right? So the first linear term will give me FSR, and then the second will give me the delta FSR. Okay, I hope that's clear. No? Sometimes, I mean, you can also write it in terms of angular frequency. Omega m is some omega naught plus m times omega FSR. So this is sometimes referred to as V1 times m plus then this second order term is referred to as D2. So D2 tells you how much the FSR is changing with mode number, which depends on the GVD. And D1 just gives you the FSR. Next, so is this clear?
Yes, sir.
Okay. So that's how my cavity resonances will be placed if I have anomalous dispersion in the cavity. Okay. Now let's look at sort of just one resonance. So let's zoom into one resonance and look at that in a little bit more detail. Right, so basically our sort of main goal here is to see like get expressions, for example, for the threshold pump power, the signal and adder frequencies which will lays, right, and how those depend on the cavity parameters, right. So that's why we are sort of analyzing this cavity in detail using its dispersion properties, and we'll see how it translates to the OPO process. Okay, so now let's just look at one resonance. So let's zoom into one of the resonances. So this is, let's say, the mth resonance, right? So it has, of course, some line width. So let's look at a point which is delta omega or delta nu away from the peak or the center frequency nu m. So again, let's go back to this expression of the power in the cavity as a ratio of the input power. Right, so as I'm changing the frequency, so this x-axis is frequency, right? So depending on which frequency I'm at, right, and y-axis I can plot as basically the power in the cavity, right? So if I'm right at resonance, so if delta nu is 0, then the power in the cavity is maximum, it's enhanced by the finesse. So this expression here was finesse right. So on resonance, this phi r is again a multiple of 2 pi. So this argument the sign term goes away, and then Pc is sort of f by pi times P in. But as I go away from the center resonance frequency, then basically this argument of the sign is not a multiple of pi anymore. So you get some contribution from this term, right? And then the power enhancement goes down. Okay? That's why you're getting this shape. So basically, this power in the cavity is a function of this detuning delta nu from the center frequency, right? Which is coming basically because this round trip phase here, that's a function of the center frequency. Okay, so this round trip phase, so at this point, frequency nu here, which is nu m plus delta nu. So again, that's beta, so propagation constant, at that frequency times the round trip length of the cavity. And now again, this beta at omega m plus delta beta, we can use the Taylor expansion. So this is beta at omega m plus beta 1, the first derivative of beta, times delta omega. Right, and the beta at omega m, that's so the beta m times LR. This we know is 2m pi, right? Because this is basically pi r at mu m, right? That's the center frequency here. So by definition, the round trip phase is 2m pi, right? Okay. So basically, we want to put this phase in here, right? So that has so that phase is some 2m pi plus some number. So this when we plug this expression in here, you can see that the 2m pi. So I'll get something like sine square of m pi plus this, right? Which is the sine square of that. So this term doesn't matter because it's the multiple of pi, right? So that means I can write for a detuning delta nu, the power in the cavity is beta 1 delta omega LR by 2, right? So only this term survives. And then we again, so now we make an approximation that for a good cavity again, this line width is usually very small, right? So this line width is basically inversely proportional to this finesse, which is related to the reflectivity, transmittivity, or the loss, right? So basically, we say that this argument is very small. So we are looking at small detunings from the center frequency. So we make this approximation of sin x approximating as x, right, for small values of x. Okay, so we are saying this argument within the line width here, this argument is very small, and that's a better approximation for good cavities, right, where the line width is narrow. So basically, yeah, we just get rid of the sign and just keep that. So okay, so yeah, just left with that. And so recall this, we are getting beta 1 times LR, right? And recall that the FSR is basically 1 over beta 1 times LR. So beta 1 LR we can write as 1 over the FSR. So basically you can write this as okay, so I've just replaced beta 1 LR as 1 over nu of SR. Okay, so this pi is also cancelled out. And so basically what you're left with is this sort of line shape, which should be familiar. So this is a Lorentzian line shape, right? So 1 by 1 over x squared. So you might have learned previously in some optics course that cavity resonance is, the shape is given by a Lorentzian, right? So, but you can see that it's actually not exactly a Lorentzian, but under this approximation of a good cavity, right, when we replace this sign by its argument, then we end up with this Lorentzian line shape. Okay, so this, the line width of the Lorentzian is this small delta nu, which is nu FSR by the finesse. Right, so this is the Lorentzian line shape. This is the line width. Right, so basically what we are saying is, so I have delta nu equal to this d nu by 2. The power enhancement in the cavity goes down by half. This becomes 1. The denominator we get 2. Right? So from the peak it goes down by half. So if I look at the full width at half max, so this is 1 and this is half. So if I look at the full width at half max of the resonance, that's delta nu for this T nu. Right? So this is the FWHM of the cavity resonance, or also called the line width. Right? So again you can see that if I have a high finesse, which means low loss, right? Low mirror transmittivity, low loss in the cavity, then finesse is very high, which means that this line width is very small. Right? So a good cavity will have a very narrow line width. Right? And the line width scales inversely with the finesse. So the more round trips the photon makes in the cavity, the narrower the resonance. And actually the higher the enhancement in the cavity, because that also goes as finesse. Right? Okay. So there's another term which is defined, which is sort of just analogous to the finesse, and that's called the quality factor. Okay, so the quality factor of a cavity, that's defined as the resonance frequency divided by the line width. Okay. So the finesse here you can see is the FSR divided by the line width. Right. So if I draw the resonances here, this is FSR, the line width delta nu, and this is nu m plus 1, right? So the FSR divided by the line width is the finesse. The quality factor is defined as the resonance frequency divided by the line width. Okay, so you can see that of course the quality factor will be a much bigger number, right? Because this is the absolute frequency divided by the line width, whereas finesse is the FSR divided by the finesse by the line width. So finesse we saw for a good cavity is usually in the few hundred range. So of course the quality factor is related to the finesse. You can just see from here, right? So if I write this d nu as nu FSR by finesse, then I get Q as this. And nu m by nu FSR is roughly just the mode number, right? That's the mth resonance frequency divided by the spacing between the resonances. So that's roughly just the mth n, right? Nu m by nu FSR. So the quality factor is roughly the mode number times the finesse. Right, so this mode number was basically how many multiple of 2 pi phase you are getting, right? Or in other words, you can think of how many wavelengths are fitting within the round trip of the cavity, right? So this m is usually, even for micro resonators where the diameter is sort of 100 microns on that scale. So the circumference is about roughly, let's say, a millimeter, right? So this m is typically a big number, like 1,000 or so, even for the smallest cavities. For bigger cavities, it's even bigger, right? So the Q is the factor of the mode number, which is around, let's say, in the thousands times the finesse, right? So if the finesse is in the range of 10 to the 3 to 10 to the 4 for good cavities, so m number is usually, we are in the 10 to the 3 range. So you can see that the quality factor usually for very good cavities we can get like in the million range. Okay, so the physical like the physical manifestation of this finesse was basically how many round trips the photon makes in the cavity, right? What is the physical meaning of this Q? Is basically how long the photon stays in the cavity. Okay, so it's almost the same thing, it's just sort of measuring in different units, right? So Q basically measures how many cycles of the electromagnetic wave does the photon stay in the cavity before leaking out, right? So if it stays for 1,000,000 cycles, then depending on the frequency of light, so you have some frequency omega, right? So then the time period of the electromagnetic oscillation is 2 pi by omega, right? And then times 10 to the 6 is basically how long the photon stays. So let's say I abruptly turn off my input power. So I abruptly turn off my input power to the cavity and then look at what happens to the power in the cavity. Then typically you will see that the power in the cavity doesn't immediately go to 0. It decays with some time constant. Okay. And so this time constant is related to this quadratic vector. So if I write this as some e to the minus t over tau cavity, that's the cavity lifetime. Basically the time scale over which the photons are leaking the cavity, or the energy is leaking from the cavity. And this tau c is basically omega over q. Or other way around, q over omega. Also, if you're looking at the mth resonance, is the mth resonance frequency. Okay, so the higher the q, the longer the photon stays in the cavity, so the energy leaks out more slowly. Okay. Equivalently, the photon is making more round trips. Right? Same. So,
So there is a difference between so m is the number of modes, but it is not the number of times it makes the round trip. The photon makes the round trip.
yeah, that's finesse. Right? Finesse is the number of round trips, and then m is the mode number. So you're operating at some particular frequency, right? So let's say your wavelength is 1 micron, right? That corresponds to some frequency, right? And then depending on the size of the cavity, etc., right, you have some FSR, right? So recall FSR depends on the LR, which is the size of the cavity, right? So depending on the wavelength you're operating at and the size of the cavity, you get some mode number at which you're operating.
Okay, sir.
Right? And that typically lies in some high number, right? So if you can imagine, if you have a very small cavity, then your mode numbers will be smaller, your FSRs will be larger, right? FSR was inversely proportional to the length of the cavity. Smaller cavity means higher FSR and smaller mode numbers for the same wavelength.
Okay, sir.
Okay, so how do you get this exponential dependence? Also, you can see from, so this Lorentzian line shape is sort of the frequency response, right? So that's the frequency response, and the corresponding time response is related by Fourier transform pair, right? So time response would be the Fourier transform of the frequency response, and vice versa. So I don't know if you remember or recall if we've done previously that if you have an exponentially decaying time response, then the Fourier transform or the frequency response is a Lorentzian. So you can just also try it at home yourself. Just take this time domain signal and then take the Fourier transform. You should get some Lorentzian line. So again, this line width is related to this tau c, right? Because so tau c is given by q, which is related to f, which is related to the line. Right? So, in other words, this line width is inversely proportional to tau c. Right? So, the longer the cavity lifetime, the longer the photon stays in the cavity, the smaller the line. Actually, it's sort of just given by that, because 1 over time is basically frequency, right? Basically, the line width is basically the inverse of the cavity lifetime. Okay, so let's see how are we doing on time. Yeah, maybe we'll stop here. So basically, we discussed the cavity properties in the presence of dispersion, anomalous dispersion, etc. in detail, right? So now we'll see what happens in the OPO process itself, right? So in the OPO, what we are doing is pumping at one of the resonance frequencies. Okay, so we have these cavity resonances. Right. So as a function of frequency, we get these so resonances, right? Nu m plus 1. And then for the OPO, basically we choose one particular resonance and pump. So omega p or nu p we choose to be one particular cavity resonance frequency, right? So we pump at that resonance frequency, and then we want to generate signal and idler, right? So we know that for the four-way mixing process, so energy conservation demands that 2 omega p is omega s plus omega I, right? Which means omega s and omega I are symmetrically placed about omega p. So on one side at some resonance, so we want to generate, let's say, omega s here, and then symmetrically about you want to generate omega I, right? So but there is, I guess, one issue here, right? So we saw that when we were discussing this for a mixing process to get phase matching. So recall we had this quantity delta beta total, and for phase matching we wanted that to be 0, right? And we saw that to get that, basically we wanted anomalous dispersion, right? In our video. And now we've seen in a cavity, right? If there is a ring cavity made out of a medium which has anomalous dispersion, then the FSR is actually not constant, right? And specifically for anomalous dispersion medium, the FSR increases with frequency or mode number, which is what I've tried to show here. So right at low frequencies, the FSR is smaller. As you go to higher, the FSR increases. Right. So now you can see that, let's say I wanted to generate signal and idler. So from energy conservation, we want that the signal and idler should be equally spaced about the pump, right? But that means that, so if my signal and idler,
Sir, can we do it other way around? Like we can put omega s in the left side and omega I in the right
yeah,
side.
this is just terminology, it doesn't matter, right? You can call this
Okay.
omega s and
Okay, sir. Okay.
yeah, so but here the point is that we want the signal and idler are generated or also at some cavity resonances, but they have to be symmetrically placed about omega p. So this delta omega has to be equal, right? But if the FSR is not equal, or if the
Yeah,
FSR
it
is
won't
not
be
equal,
equal.
yeah, so specifically, let's say you have this case of anomalous dispersion, FSR is increasing. You can see that if I go 2 resonances away from the pump on this side, this spacing will be much or will be bigger than if I go 2 resonances low, right? So basically, I cannot satisfy this energy conservation if I have dispersion in my cavity, right? So that seems like a problem, right? I need anomalous dispersion to phase match the four-way mixing process and make it efficient, right? But in a cavity, if I have anomalous dispersion, then the resonances are not equally spaced. And if the resonances are not equally spaced, then I cannot satisfy energy conservation, right? So that seems like a problem, but yeah, in next class we'll see in more detail how it all actually just solves on its own.
Okay, sir.
Do it possible to get the anomalous behavior in ring resonator also?
Yeah. So this anomalous dispersion is a property of the waveguide, right? So typically, like you have some cross section of the waveguide, right? So you have some material here. So this is some core material. Then you have some cladding. You have some substrate. So depending on the materials and the cross section you use, you have some waveguide with some dimensions, right? Which decides the modes which are supported and propagate, which decides the n effective of those modes, right? Which basically gives you the dispersion of the medium, right? So the dispersion is basically given by the design of your waveguide device, right? So the materials, so it could also be an optical fiber, for example, right? So some core and cladding. So it's a cylindrical geometry, but the idea is the same, right? So the dispersion just depends on the material of the core cladding, the size of these core and cladding, etc. And now what we are just doing is just wrapping it around, right? So just wrapping it around and making it a ring, right? So the dispersion properties of my ring cavity are still given just by what waveguide I started out with, right? So sort of the cross-sectional dimensions of the. I'm just wrapping the waveguide into a ring. So.
Okay, sir. Because while I was simulating this ring resonator on MATLAB, so I was ignoring this thing V2, beta 2.
Yeah. So for example, when you take some materials here, right? So the refractive index of the materials will depend on the wavelength, right? And then the modes that you solve for, their effective index will also depend on wavelength, right? And so when you plot these refractive indices versus wavelength, you will see that I mean, in general, you will get some beta 2 and even higher orders of beta also, right? So you can try to design your waveguide with materials in cross section such that you try to get beta 2 close to 0 at some particular wavelength you are interested in, right? So that's
Okay, sir.
dispersion engineering that. Yeah. So in this case, basically, we want anomalous dispersion because we want the four-way mixing process to phase match and be efficient. Yeah. So yeah, we'll see next class how this sort of this conundrum gets solved on its own. It's not actually a problem. It's actually. I mean, it turns out that if you had equally spaced resonances, then that's actually bad. You want this kind of. So a clue is basically, so if you go back to our four-way mixing, why we wanted this anomalous dispersion was because we were getting nonlinear phase shifts, right? The gamma p terms, and we finally wanted something like delta b, delta beta, the usual delta beta. So 2 beta p minus beta s minus beta I should be equal to some 2 gamma p, which is the nonlinear phase. Right? And in our analysis of the cavity so far, we've just assumed we haven't taken any nonlinear phase shifts, right? We just took some round trip phase and equated it to 2 pi and all that. So this is just the bare cavity resonances that you get from its dispersion property. But when you factor in the nonlinear phase shifts, it turns out that this problem gets solved. So we'll see next time how that happens.
Okay, sir. Thank you, sir.